Hey everyone, my name is Tim Beiko and I work with the Ethereum Foundation. Today I'm going to take some time to chat about how Ethereum works after the merge and what's next on the roadmap for the protocol. So high level, I'll start by kind of explaining how we actually got to the current proof of stake design. What were all the rounds of iterations that sort of had to happen for us to end in this final state. Then I'll go over how the merge actually happened, like from a technical perspective, what was involved there. I'll show a couple charts that kind of put in context how Ethereum looks after the merge. And I'll end by taking some time to go over what are the next things that are being planned for Ethereum. So to start from the design evolution around proof of stake. When we talk about the merge and proof of stake, a lot of people will often say that, the Ethereum people have been working on this for many, many years. What took so long, complicated to ship this. There's other chains that are on proof of stake. And so, what happened there? And the thing that's worth understanding there is that it's true that Ethereum always wanted to move to proof of stake. It was always part of the roadmap, even before Ethereum launched. But we almost did this in 2018, and we ended up instead scrapping everything we had built basically up to that point because we weren't quite happy with the design. So around the end of 2018, we had a proof of stake design that was almost ready to go live, but there were a few issues with it. The first was that it was kind of implemented as a special smart contract on Ethereum with different rules, and there was a lot of complexity associated with managing this like different smart contract that has to follow rules and differently than every other contract on chain. The other problem with that is that because everything was done on chain, it was a really high minimum stake at the time, which was 1,500 ETH. Even if in 2018 it wasn't as big of an amount as it is today, it was quite significant, and today would be pretty terrible if that was the minimum stake required. And then lastly, there was a lot of parallel work happening on sharding that was hitting similar kind of problems as the proof of stake work. So late 2018, early 2019, there was the decision made to just instead ditch all of the work that had been done and think about what would Ethereum on proof of stake, fully sharded, look like if we just started it from scratch and kind of rebuilt it from first principles. And this is where sort of the Ethereum 2.0 roadmap was born. And many of you have probably heard about this, but the idea there was that there would be three phases. The first, which we called phase 0, was to launch the proof of stake chain separately, which is the beacon chain. Then once we had that, we would anchor data shards to it, which would allow us to shard storage on Ethereum and provide kind of a cheaper way for applications to use that. And finally, once we had the whole system running with the beacon chain, with the shards, we would then turn on computations. And so these shards could also help us scale execution. But there were still some problems with this. The first is that on this last point, when we say we would turn on the computation in the shards, we never got a final design that we were quite happy with that. It was never kind of figure out how you would do this in practice. The second issue was that this would be a painful migration for users and application. They'd have to go from the current existing chain all the way to a new one and move everything over. And then lastly, this would be a problem because it would require brand new software to execute all these transactions and all of this sharded computation. And by that point, we'd learned it's really hard to write this software. So we had all of the ETH1 clients, all of these new beacon chain clients, and thinking we'd have to write a whole other set was quite a big task. But luckily for us, in the meantime, we started to see rollups appearing. And this helped us kind of refine our roadmap to leverage rollups much more. So there were a lot of posts on ETH Research between 2019 and 2020 that kind of had multiple iterations on this. The first one was this idea of, once we realized that this full sharding design would take a long time and we were still on proof of work, Vitalik had this first post proposing an early merge, saying, is there a way, we could just move to the beacon chain earlier, get rid of proof of work, lower issuance, lower energy use, and kind of be at least closer to the end system. And then a few months after that, or actually, almost a year after that, there was this other idea around Rollup centric roadmap. And this is what I was hinting at, where in that time, we started to see rollups like Optimism, Starkware, ZK Sync kind of go live and launch and get users. And the idea was, well, what if, the idea at that point was like, well, what if instead of relying on the protocol itself to scale, we simply relied on rollups to enable this? And that would kind of take out the most complicated part of our roadmap, this entire execution, which was this entire execution sharding, and we would instead depend on rollups for that. And then the last kind of iteration to this specification that we had was this idea of executable beacon chain put forward by Mikhail from the consensus team. And his point was that the software we had today running Ethereum ETH1, the proof of work chain, was already able to switch to a different consensus algorithm. So Ethereum was running proof of work, on mainnet, but it uses different consensus algorithms on test nets or in private networks. And so this final idea was saying, well, what if instead of, building all this new software, we simply kept everything and told the clients on the network to simply switch from proof of work to proof of stake as a consensus algorithm. And that was really kind of the early draft of what would become the entire merge spec. And so if you look at it from a higher level, you can kind of look at what the old roadmap was like and what the new one currently is. And you don't need to understand everything in these diagrams, sorry. The main point I'm trying to make here is just that they're roughly the same, even though it's a completely different approach. So if we look on the left side, there's this Ethereum 2.0 diagram by Xiaowei, which was popularized in 2018 and 2019. And it kind of shows you, we would have, that actually still kept proof of work for a while, but we'd have the beacon chain that would be providing kind of the proof of stake algorithm. We'd have all these shard chains providing data, and then within them, we would have these virtual machines that run end user computations. And then all of this would be kind of orchestrated by the protocol itself. If you look to the right of this, this is a diagram by ProLambda from the Optimism team that's from this year. And the idea today are still quite similar. So we still have proof of stake that kind of runs all of the consensus of the system. We also have this EVM that's still running, all of kind of the applications on L1. And you can think of this as like analogous to the proof of work chain on the other diagram, but this one doesn't require proof of work. It's all running under proof of stake now. And then we still want to keep this idea of sharded data on the network, which are now called blobs. You can see them there. So this is equivalent to like this third row on the other graph. And then on the last row, you can see we have all these EVMs also providing kind of a high level of scalability and computation. But the difference here is that instead of being all part of the protocol, like we had in the original roadmap, you can think of these as all different L2s, which post their data back to the blobs in the protocol, but basically are independent ways of scaling Ethereum. So you can imagine the blue one being Optimism, the yellow one being Starkware, the green one being Arbitrum. So you have all these different kind of EVMs that are running in parallel and scaling computation. And so anyways, to zoom out again, at a high level, by moving to this Rollup centric roadmap, we kept kind of a very similar design. We achieved all of similar goals, but we kind of moved this most complicated part of like sharded execution from the protocol to having it be kind of owned by outside teams that are layer 2 teams today. And so, it's nice to talk about all of these kind of design considerations and whatnot, but it's worth also hitting on like, why did we move to proof of stake? Like, what do we get out of this? And there's really 4 main things. The first is finality. So in proof of work, you never get a block for which you can be like highly confident it's not going to reorg. It's always like a probabilistic finality, meaning that, the probability of this block reorging kind of approaches 0, but it's never quite 0. And there's not a certain block at which you can say, okay, things kind of change here. In proof of stake, once we have 2/3 of a block, 2/3 of validators that have like confirmed the block, which takes every 12 minutes, we consider this final. And what this means is that for this block to be reverted, you would need at least 1/3 of the stake to be willing to burn their stake. So this gives us like a very discrete point in time where we can say, look, at this block, there's this amount of like economic security, and then applications can use this as a way to move forward and to know when something is confirmed. The other thing that's really interesting with proof of stake is that we can reduce Ether issuance. And the reason for this is that in proof of work, we need to issue a lot of new coins because there's no way to penalize miners for doing the wrong thing. The only thing we can ever do is like give them a big incentive to do the right thing. But then if they choose to defect, they only have sort of an opportunity cost. They don't get penalized beyond that. And proof of stake, because we introduce penalties and slashings, we can lower the amount that we pay to do the right thing, because we also have these bounds, kind of these protection that'll take people's stake away if they do the wrong things. And this means that, because we sort of move from having just a carrot to having a carrot and a stick, we don't need as big of a carrot to incentivize people to do the right thing. And in practice on Ethereum, this creates about 10 times a 10x reduction in issuance. So we went high level from issuing about 15,000, 16,000 ETH per day under proof of work to about 1,500 to 1,600 per day under proof of stake, give or take. Another really nice benefit of proof of stake is that there's less economies of scale than there is in something like proof of work. And what this means is that in proof of work, if I'm mining alone in my house, I have a really kind of bad setup, because my cost of energy and my cost for my miner does not get amortized over like a ton of equipment or a ton of like infrastructure. Whereas if you're kind of setting up an industrial miner and you have like a whole warehouse of them, you have a special deal for lower electricity costs and whatnot, you can get really good economies of scale. And proof of stake, everybody runs the same software, and there's not really much you can do if you're running, 10 versus 100 versus 1,000 validators. There's a couple of small things here and there, but the degree of economies of scale is much, much lower than in proof of work. And then lastly, the biggest bit is that there's no environmental impact with proof of stake. So proof of work is like this competition to invest more and more resources to secure the network. So as the network becomes more valuable, you raise the incentive to kind of take even more physical resources to secure it. In proof of stake, because we use virtual capital, so like there's no physical resource that's securing the network. And so we don't need to have this huge environmental footprint to keep the network safe. So now that we've kind of looked at the design and how we got there and why it matters, it's worth zooming in a bit on the actual merge itself, like what happened there and how do we transition from one side to the other. And at a high level, I briefly mentioned this. The idea was to go from using proof of work to using proof of stake as the consensus algorithm for Ethereum. And after that, what was known as ETH1 sort of became the execution layer of Ethereum, and the beacon chain, which was already running in parallel, became the consensus layer. And again, like I said, these execution layer clients already had the ability to swap consensus algorithm like we see with POA networks such as testnets or private networks. And the way we triggered this transition is saying, once we hit an amount of difficulty on the network, and difficulty is basically how hard it is to mine a block in proof of work. Every block has a specific difficulty, but it also keeps track of the total difficulty of its entire history. So from Genesis all the way to that block, what's the sum of all the difficulties? We call this the total difficulty. So what we said is once we hit a specific total difficulty on the proof of work chain, that would be the trigger for proof of stake to take over. And then after this transition, you would have the consensus layer, which would still run the proof of stake algorithm, which kind of agrees on the head of the network and the latest valid block. The proof of stake bit is also what's producing in gossiping blocks, and then syncing across different forks when there are some. And then we keep all the execution layer software to actually execute the EVM. So when you get a new block on the proof of stake side, there's transactions in it. You want to make sure that all those transactions are correct. So the execution layer is still in charge of that. It would also manage all of the state. So all of the kind of where the smart contract and balances are stored, and deal with syncing and storing that in a database. And finally, it'll also keep tracks of transactions and gossips transactions before they're actually included in blocks. And if you kind of look at like what does a single block look like after the merge, this is a quick overview by Danny that you see on the side. If you look on the outer layer, this consensus layer bit, you can think of this as like consensus metadata, where you keep track of all the information related to proof of stake, what slot we're on, the current validator signature, the random mix, the random value, all of the attestations that you've seen, all of the deposits that you've seen, the exits that you've seen. But there's no like actual end user transactions. We introduced those as part of the beacon chain in the merge, and the way we do that is we just keep the parts of the proof of work blocks that have the data related to transactions, which is this execution layer block that you see in there.
And it has stuff like obviously the list of all the transactions, but also things that are necessary to figure out the validity of those transactions, like the base fee and the state root. And the idea there is that like as little as possible should change. So block times were one of the small things that changed. It went from about 13 seconds to exactly 12 seconds, except if a validator is offline and misses their block, which happens less than 1% of the time. We had to set a bunch of fields to 0 because they kind of related to proof of work. So we talked about, like the total difficulty, things like that. All of that, we just decided to set to 0. And then lastly, there's one thing that we didn't want to set to 0 is the difficulty opcode. So the difficulty opcode would return the difficulty value of a specific block. And people would use this as a source of randomness. If we had this for 0, it would obviously break a lot of contracts. So what we've done instead is, even though the difficulty of a block is 0, we changed this opcode return value to return the value of the randomness output of the previous block on proof of stake. And so that gives you kind of a value that you can use in a smart contract. And if you zoom out a bit more, this was kind of within a block. If you look at the level of the software itself, we still have kind of the same components of software that we would use before the merge. So before the merge, you could run a node on the beacon chain or the consensus layer, and that would do, it would track the head of the beacon chain, gossip in the Tesla's block, receive validator rewards and all of that. There's also the software you would use on the proof of work chain, which is now the execution layer, which, as we said, processes the block, maintains the mempools and whatnot. So you keep both of those. They both kept kind of their APIs. So if you were using JSON RPC or the beacon APIs, nothing changes there. They both have their separate peer-to-peer networks, so they're connected with peers on their own network. And the one thing we introduced was this idea of an engine API. And so the engine API is basically used as a communication layer between the beacon node and the execution layer to do things like send or request blocks when you need to execute transactions in them. But that was really kind of the only minimal change we made, such that like these two pieces of software would work together. And then lastly, if we look at how the actual transition happened on the network, there was like 3 steps that happened. The first is, like we mentioned earlier, we wanted to listen for this terminal total difficulty trigger. So once a certain amount of total difficulty was seen on the network, we would trigger the transition. Once we see the block exceed that total difficulty, we would consider this to be the last proof of work block and then move all of the responsibilities to creating blocks to the beacon chain. And then finally, like we mentioned earlier, what's nice with proof of stake is you can have this finality property where you're pretty much guaranteed to not have a reorg beyond that. So we wanted to make sure that this first post-merge block was finalized on the network before we considered the transition complete. And again, thanks to Danny Ryan for these graphs, but here's what it kind of looked like at the network level. So if you go all the way to the left, you have a proof of work block, a beacon chain block. On top, the proof of work block has like proof of work and then all of the transactions and transaction related fields. On the bottom, you have this beacon chain block, which has all of this kind of proof of stake data. So things like the attestations and deposits and whatnot. And so, on this first block, they're both separate. The merge hasn't happened. If you move one block to the right, you could think of this second proof of work block as the last proof of work block. So this is the one that would have exceeded the terminal total difficulty. Again, nothing changes in that block specifically. And underneath it, the beacon chain is not doing anything yet. But in the block after that, so the third block on the right, this is basically the first post-merge block. So you can see the beacon chain still has all of the proof of stake stuff like it had before, but now it's also including the transactional data from the execution layer. And then this fourth block on the right, you can see it basically has no more link back to proof of work. So, this is a world in which we're fully operating under proof of stake. And that was basically it. That was like the transition from proof of work to proof of stake. It kind of happened instantly between 2 blocks, last proof of work one, and then the first proof of stake just got triggered for the next validator. And a few nice things that we observed on the network after the merge. So first is just like the energy bit. So I think this chart kind of speaks for itself. If you look at the energy consumption of Ethereum, you can see from like January 2021, it growing pretty quickly. And then, it sort of drops down to basically 0 after the merge. So that's obviously a huge change. And then the thing that's really neat as well is this idea that we've moved to a more stable block regime. So before the merge, when using proof of work, we could only ever like target a rough average time for blocks, but we couldn't get high confidence that the blocks would come up exactly at that interval, because proof of work is a very random process. So you can see on this graph, basically when the merge happens, is when we go to this straight line where like blocks are basically coming every 12 seconds, except in the case when the validator is offline, and they come every 24 seconds. But even if you consider 24 seconds, you know, your worst case should be like this second dotted line that we see on the right side of the graph. You can see that proof of work was just so much worse on that regard, because there's many times when blocks would come much later than even 24 seconds. So it's really, proof of stake's really given us like a much more stable network on which to build. Okay, and then last part of my talk I wanted to cover is what's next after the merge. You know, we've done this, what are we working on now? So at a high level, this is still being decided. You can think of this as having two buckets. One is like the stuff we've already agreed to do, and then the things that we're still kind of debating, and hopefully in the next month or two, we should have more clarity on. But first is, you know, first, this network upgrade after the merge is going to be called Shanghai. And so these are the things that have been like confirmed. There's one big thing, three small other changes. Then we'll cover the stuff that's still being discussed. The biggest one is just withdrawals from the beacon chain. So the merge did not enable these. The reason for this was the merge was already the most complex change we did to Ethereum. So we wanted to make sure that we kept the complexity as minimal as possible, and withdrawals were just one thing we could completely remove. So they're obviously now the #1 priority, and they'll be part of the next network upgrade. Then these next three things are just very small changes we can add alongside this that make a kind of a good difference for end users. The first, the Swarm Coinbase EIP, basically a few years ago, we changed the cost of accessing different data on Ethereum based on whether it's already in memory or if you have to go read it from disk. The Coinbase address is one where we just forgot. So basically, you have it in memory when you produce a block, because you get that address from the block. And we would still be charging it as though we had to read from disk. So it was kind of overpriced in that regard, and so we'll be lowering the cost in that upgrade. Kind of similarly, we're introducing a new opcode called push 0, which just pushes 0 onto the stack. And the idea there is that a lot of time people want to push the value 0 to do things like padding and whatnot. And we're introducing just like a different opcode that makes it cheaper to push the value 0 onto the stack. And then lastly, we are adding a cap on init code size for smart contracts. And we're going to start charging gas for this as well. So this is something that was not there in the past, and it'll kind of add a bound on that resource in the system. So again, withdrawals are really the biggest things here, and there's three more kind of small changes that have been confirmed. In terms of everything else, these are all things that are being discussed right now, and the big question is, you know, should we do them now? Should we do them in the upgrade after Shanghai, and how do they all fit together? But basically, there's 5 of them. This first one is EIP 4844, which you might have heard of as proto-dank sharding. This is an EIP which provides the first step of data sharding. So like we saw earlier, which is a temporary data storage solution for rollups, and it reduces the cost of transactions on rollups significantly. So that's something obviously everyone wants to see. It's a pretty complex change, so we're still debating when is the best time to roll it out, and with what. The second one is the EVM object format. So this is an entire set of EIPs that introduces a new type of smart contract, which can have different EVM rules, which allows you to enable or disable specific instructions to kind of enforce specific formatting in the code to get some better efficiencies once you're doing things like static analysis and whatnot. So this will provide like a whole array of new tools for smart contract developers. And then another EIP that's being discussed is 1153. This EIP basically proposes to introduce transient storage opcodes, so tload and tstore, which you can think of as alternatives to sload and sstore that are cheaper because they're cleared out at the end of the transaction. So they're kind of like the name says, transient storage that just can be used for things like setting locks and whatnot on specific storage slots within a single transaction. And then another one that's being discussed a lot is EIP 47 0.58, which deactivates self-destruct and converts it to an opcode named send all. So if you called it, you wouldn't destroy the contract, but you would get all the money sent to the caller like you do with self-destruct now. And the reason for this is kind of twofold. One is self-destruct has an unbounded execution time with a fixed gas cost. So self-destructing your large contract costs the same as self-destructing your small one. And there can be massive differences in how long it takes the node to actually compute that. And the other challenge is that we want to move to a different storage model on Ethereum called Vertical trees, which enables us to scale on the execution layer. And self-destruct doesn't work really well with that. So it would be good to remove it. But it's an opcode that's widely used, and we want to think very carefully about the impact on existing contracts if we do something like this. And then the last thing that's being considered, and that's sort of been considered on and off for many years, is the idea of BLS precompiles. So the Ethereum beacon chain uses BLS signatures, and right now there's no way to verify a BLS signature on the execution layer. So adding a precompile to do this would enable a ton of use cases around staking pools and whatnot. It's just something that's kind of a question of relative priorities, where everybody thinks at this point it's something we should have, but whether it's like the most important thing to do now is still being discussed. So that was it. Hopefully it was helpful. It gave you an overview of how we got to the merge, how the whole transition happened, and what we're thinking about now with regards to Ethereum. If you have any questions or comments, feel free to reach out on either Twitter at Tim Beiko or to send me an email. I'm always happy to chat about this stuff. Thanks a lot.
Thanks, Tim. Really appreciate the presentation from the Ethereum Foundation and the in-depth review of Ethereum after the merge. It's really valuable to have you guys always supporting our event. It's already the end. This year, again, we had massive support from companies building on Ethereum. So we are very glad to have them coming back year on year to tell us about their progress and the exciting stuff that they are building on Ethereum. So as you know, Atato is not an event organizer, but we really care about the community. So if you want to reach out and you want to set up some meetups and so on, please feel free to do so. Also, as you know, we are a custodian, so we offer crypto custody for Web3 projects and any companies basically holding some cryptocurrencies. We do stuff a bit differently, and with us, it's quite easy to onboard and to start to secure your crypto properly. So if you want to reach out, please feel free to link with us on our website or any social media. We are licensed and regulated, so happy to discuss with you both. After that, there will be just a QR code. You can just scan it and try our app yourself. And once again, I really would like to thank everyone who participated to this event, all the attendees, but also the panelists, and a big thank you to the Ethereum Foundation for the support for this event. So thanks again for joining, and we'll see you next year. Thank you. Bye-bye.